This lecture is about problem boundaries. We want to make sure that you have the ability to recognize in problem solving or when you're thinking about a situation where to apply what concepts. And this will also help tie in what we've already learned with this new section of dynamics, which is just Newton's laws of motion. All right, so far we've talked about the boundaries of projectile motion versus uniform motion versus freefall motion. When we study motion, we looked at uniform motion, which is just motion with no acceleration and no forces. One of the examples that we used when we talked about uniform motion was the concept of reaction time. When you are in your reaction time, before your body has an actual opportunity to react, you're experiencing uniform motion. And then there's uniform accelerated motion. Any motion where the acceleration is uniform, constant acceleration. In this case, there must be a force present to cause an acceleration. An example that you could use for uniform accelerated motion would be the instance after the reaction time when you actually slam on the brake. You're applying a force, therefore the acceleration is constant. Likewise, you could use uniform motion and uniform accelerated motion for a projectile. But we haven't had an opportunity to study any situation in which there is non-uniform acceleration. So that's been a boundary. We haven't been able to consider what happened before an object was in free fall. What happens before the acceleration becomes average and the force becomes average. There are still forces present, but since the acceleration isn't constant, we could not use our kinematic equations to solve for non-uniform acceleration situations. So here's an example that we could use. In this example, Benny is flicking his friend Scorpion over the edge of a table. You see, we can't, using uniform motion and uniform accelerated motion, we can't consider this instant right here in which Benny is doing the flicking of the scorpion. Our boundary up to this point in time has been from the moment that the object is experiencing uniform accelerated motion in the y direction and uniform motion in the x direction to the moment that the scorpion hits the ground and a force up is applied that stops it. So that means that before studying forces and dynamics, we've only been able to consider this section of the pathway, and we use uniform motion in the x direction and uniform accelerated motion in the y direction, making projectile motion a two-boundary situation where you have to know that vectorially you're separating it into components, the x component and the y component, where if you're given some initial velocity, the velocity in the x direction would be the x component of that velocity, and the velocity in the y direction would be the y component of the initial velocity. We cannot consider what caused that velocity, what gave it that velocity, and we cannot consider what causes that velocity to change at the end either. We can only use uniform motion and uniform accelerated motion to study the pathway of motion of free fall and projectile motion. What we're going to learn is we're going to learn these boundaries now. All right, this is when a force changes motion, but it does not necessarily experience uniform accelerated motion. And again here, a force changes motion, but the acceleration is not necessarily uniform. So these situations here and here are going to take into consideration a way to solve for acceleration, or the way to consider acceleration, or a way to look at the motion that's happening or the source of the motion using something other than kinematics. So these situations here, we would be able to solve without kinematics. which is pretty darn convenient because we don't always want to know about the change in velocity. We don't always want to know about the change in position. Sometimes we just want to know, well, what caused the object to start moving in the first place, or how can we expect the object to change its motion depending on what happens. So this is a new and kind of neat situation to look at. So let's take a look at our boundary so far. And our boundary has been we have not been able to answer the question, what causes motion? We have not been able to answer why do objects move the way that they do other than free fall. We have not been able to answer the question, what causes acceleration? And we have not been able to answer the question, how do you get an object to move in a circle? The true actual answer to all of these is that a force causes motion. A force causes objects to move the way that they do, or forces. Forces cause acceleration, and forces have something to do with how objects move in a circle. It's more complicated than that because, in fact, the types of forces and the directions of forces will all change each one of these components. So we call this the study of dynamics. It's the connection between forces and motion. When we study dynamics, we're going to be studying what is a force. And the answer will be any kind of push or pull on an object, whether in contact or not in contact. So some examples of this could be pressing on the gas in your automobile and accelerating forward. Then the engine would be pushing the car forward. Or it could be coming to a quick stop. In that case, friction is applied and it pushes you backward. It could be dragging a wagon across an open field. In that case, you're pulling. So there's lots of examples of forces that we can study. So we're going to talk about or restate Newton's first law, which says that if an object is at rest, starting it moving requires a force. Specifically, it requires a net force, but this is always going to be true. And remember that an object is at rest only in a frame of reference. Otherwise, we would say that when an object does have a velocity of 0, a force is required to accelerate it from a 0 velocity to a non-zero velocity. So this is an acceleration. When an object is not at rest, or you're in a frame of reference where an object is not at rest, then it's already moving. And that object is going to, if you're going to get an already moving object to change its velocity, either direction or magnitude, then you're going to require a force. Without a force, it would continue in a straight line with uniform motion, an acceleration of 0. All right, so we can come up with the general conclusive statement that causing objects to accelerate will always require a force. And that's the general statements of Newton's first law. Forces exerted in different directions will have different effects, which means that forces are vectors, which is a pretty darn exciting thing for you because you know how to do calculations with vectors. If you have a force, and we're going to call this the net force, we know that we can find the y and the x components of that force using vector mathematics. So that means that the net force in the y direction is going to be F net sine theta, and that the F net in the x direction is going to be F net cosine theta. And so that's pretty darn convenient that you're going to use the exact same vector addition to be dealing with forces. And that also means that forces have direction. So in a situation where you have a force applied even in one dimension, if you had a force applied in the positive direction and a force applied in the negative direction, even in this situation that's only one dimensional, the net force would be difference between the two forces because it's a vector and vectors have direction.